really, really grateful on behalf of myself, my group members, and my colleagues, my collaborators, especially Dr. Bill Guo and Dr. Hong Xianghuan in the audience, to thank the foundation. This is not only the financial support at a very critical stage, but more than that, this is encouragement for outsiders and beginners like us, physical chemists, to start to have some humble contribution to important problem, the pancreatic cancer research. So in the following, I'm going to tell you not only the science, but more important perhaps is my gratitude to a few people in my life so far, from the beginning of this project 7 years ago. Actually, this is an academic research initialized by the passing away of my beloved colleague, Professor Don Kiverson, a very famous theoretician in statistical mechanics in chemistry. About 9 years ago, in a day like this, he left us, and all the 45 faculty members in the entire department are so hopeless and powerless watching him dying at the moment. So at the time, I joked that I start to see my mid-career crisis, and I start to wonder what is the power of physical chemistry if we can not do anything for our colleagues. So we start with this research. On one hand, the second day, my colleague some kind of severe headache and could not give a lecture in general chemistry. He was sent to the MRI scan at the UCLA Medical Center. And at the time, I started to realize that how powerful is magnetic resonance, not only in the format of spectroscopy for chemistry, the format of solid-state NMR for material, but especially in the physiological examination for medical research, especially holy grail is the human medical research. And later on, when we work in CNSI, we realized that NMR, MRI, especially is the right time scale and the scale for human applications. So at that time, I also started to work with my colleagues in medical school. They told me the MRI is perfectly non-invasive, and also it's not expensive at all. For example, the whole body scan at the time just cost about $300. So in addition to all the good things they told me, on the other hand, I start to see the downfall of the fairy tale world, if you like. Because I start to see from the real examples, there's a severe limitation to MRI application to early tumor detection. The patient is 67 years old. Over the past 7 weeks, the patient has difficulty in talking and walking. So MRI scan from Massachusetts General Hospital, Harvard Medical School, shows that in the trained eye of those medical doctors, and we have a lot of experts here, it seems that everything is fine, no matter T2-weighted MRI scan or PET, positron emission tomography. But the symptoms just get worse and worse. So after 2 months later, another scan shows there's a big lobe of tumor. And of course, the expert here can tell me more about it. So we start with the tumor research at the time, and we start to realize that for early tumor detection by MRI, this is still a dream at the time. We can detect well at a later stage, but perhaps not at a stage, for example, 2 months ago. If you ask me what is the question, I will say it's not the signal-to-noise ratio, because you can see there's no noise at all. And perhaps it's not a problem of the spatial resolution, because with strong enough gradient, we can even see single cell. The problem perhaps is the contrast. That is, there's no difference between signal from the healthy tissue versus the signal from the lesion tissue. So for the medical doctor, perhaps they cannot catch the tumor at such early stage. So after passing away of my colleague, I learned something about tumor, and of course, no need for me to repeat how awful is this disease. Exactly at about the same time, 2003, at the passing away of my colleague, I noticed that there's a new technique new ideas start to emerge. People call it molecular imaging. For example, in 2003, there's a second annual meeting of molecular imaging in San Francisco. This is one of the slides from Siemens. It's confidential, so please don't ask me how I got this slide, okay? The idea is not to detect water like the conventional MRI, and from the water to indirectly refer to the physiological condition from the water proton density, radiation time, so on and so forth, or even diffusion. The idea is that why not? Let's directly catch those molecules, those bad molecules, then make the organ malfunction, or perhaps they serve as a precursor molecule for cancer growth, such as the antigen and the cancer cell membrane, such as the vascular growth factor, so on and so forth. You can catch those molecules directly, perhaps it provides a clue to very early detection of the tumor. The truth is that we have this dream for a long, long time, for almost 2 decades. But at the time, there are 2 major problems that had to be overcome. The first problem is that when we detect water, we are talking about 110 molar of spin concentration. But for such a small concentration of the biomolecules, be it nanomolar, picomolar, how can you detect this kind of small concentration? How do you have this kind of signal-to-noise ratio? Change number 1. Change number 2, that's even more severe. In the presence of huge water background, 110 molar, how can you distinguish the weak small signal from these important biomolecules? Because these 2 challenges at a time. So essentially, this field did not progress so well until a new idea emerges. This new idea is that why not? Let's use molecular beacons. For example, as far as magnetic resonance is concerned, why not? Let's use magnetic nanoparticles, because it can create enormous magnetic signal by affecting the spin dynamics of surrounding water protons. So by attaching this magnetic nanoparticle to some specific antibody, and then attach and target to the antigen, like pancreatic cancer cell membrane, maybe by indirectly detecting these molecular beacons, we can see those small concentration of biomolecules so well. And that's the fundamental idea behind molecular imaging. To detect the imaging, we indirectly detect nanoparticle, be it magnetic nanoparticle for MRI, be it quantum dots for optical imaging, so on and so forth. But it turned out that at the time, about 2004 and 2005, the biggest problem is not the technical problem. The biggest problem is that we could not get IRB approved for animal experiment. We tried 2 times, but just failed. So we have done a lot of computer simulations. We with co-workers to work on ex vivo experiment, in vitro experiment, but we had no chance at all to pursue even mice experiment because we just could not get IRB as an outsider in Department of Chemistry and Biochemistry. And at the moment, I met the second people that dramatically influenced the trajectory of this project. That's my colleague, and he again died of brain tumor. And he's a very famous organic chemist, and this is 2005. At some point, we see he's recovering, but still, at the end, he just passed away. And that's the moment we realized we are going to pursue this work no matter what it takes. We are going to implement the idea of molecular imaging in brain tumor, in a case, no matter what it takes. So we did something very unusual. I contacted with my advisor. He's in great illness in National Taiwan University, Department of Chemistry. And we set up a lab layer, cell room layer, and we have a mice room, so on and so forth. And then we have a NMR, we call it poor man's MRI at the time. And we also built some equipment ourselves to save the funding. So essentially, we set up a lab layer with the legal document, and we can perform the animal experiment layer. While at UCLA, we do the computer simulation and ex vivo in vitro work, so on and so forth. And when it comes to the mice experiment, we just send students to visit layer, okay? So that's the way I solved the problem. So after another 5 years until today, we developed a protocol of 11 steps to have 1 stone and 2 birds, i.e. to achieve 2 objectives at the same time. Objective number 1, to detect pancreatic cancer at early stage. Objective number 2, by the way, try to cure the pancreatic cancer, okay? It consists of the following 11 steps. But again, let me not forget the contribution from my group member, Suzy Huang. After PhD 3 years with me, she went to Harvard Medical School and right now is the residency in Harvard Medical School. Professor Dennis Huang, right now is a professor in Taiwan. John Furuyama, right now is a postdoc at UCLA Department of Radiology. Stephanie, postdoc at UCLA Medical School. Cao Xiong right now going to graduate, and James Hui is the son of Professor, my co-worker, Hong Xianghui, right now is in UCSF MD PhD program, okay? And without the guidance of Dr. Guo and Dr. Hui, this project is just essentially impossible. The procedure consists of following 11 steps. Step number 1, we create pancreatic cancer. We want to have a control experiment. So to the left is the pancreatic cancer cell line, which respond to CA19-9, this antibody. To your right is the pancreatic cancer cell line, which will not respond to the same cell line. Step number 2, we target it. Based on the bias of Dr. Hui, we and Dr. Guo, we use CA99. I'm sorry for the picture. I did not change the picture yet. That's the right picture, okay? Biomarker CA99. Without going to the details, we can find this biomarker abundant on pancreatic cancer cell membrane. Step number 3, we do some wet lab chemistry. We conjugate antibody CA99 to magnetic nanoparticle. We call it bioconjugation, and this is part of biochemistry, organic chemistry, so we are good at it, okay, as a chemist. Step number 4, delivery from IV injection. Step number 5, pathology. We wait until the tumor grows big enough, and we want to make sure that our targeted scheme is successful or not. In principle, our magnetic nanoparticle should be able to attach to the pancreatic cancer on left, but not to the pancreatic cancer on your right, just because they will not respond to CA99 antibody. How can you confirm the targeting? Well, why not? Let's see the ion stain in the following. So ion stain shows that in this kind of special dye, ion will start to show color, purple to blue. So you can see that the targeting work almost too good to be true, if you like, okay? The one can target CA99 positive, as you can see that all the ion reflect the color, but the one negative did not reflect the color at all. So this experiment suggests that CA99 for pancreatic cancer, for this cell line, is a good biomarker. Next step, our goal is about early tumor detection. So we will do everything. By this time, we try to detect the tumor at earlier stage, but we fail. As you can see that to the left is for human glioblastoma. We target by cyclic peptide, RGD. This is a well-established procedure. Maybe from the ion stain, you can see not too many magnetic nanoparticles can really label and attach to the human glioblastoma multiform cancer cells. And to the right, we repeat the same procedure for the pancreatic cancer. But you can see, embarrassingly speaking, there's only one magnetic nanoparticle. We have no idea about what's going on. But its measurement can be reproduced. That is, for the early stage tumor, no matter pancreatic cancer or human glioblastoma, the conventional wisdom of molecular imaging by magnetic nanoparticle cannot target very well. As you can see, not too many magnetic particles are really there. We have no explanation. We're just hypothesis, if you like. We assume that perhaps it related to the fact that these particles are delivered from the blood circulation, and maybe for that early stage, the bacterial growth is not good enough. That's our guessing, and we really wish experts here can give us more comments and corrections to help this project progress better later. That's the end of step number 6. Step number 7, it seems essential at this point that we need to develop a method which can help us see very dilute, very tiny concentration of magnetic nanoparticle. How can we do it? Essentially, we want to see the dipolar field introduced by external superconducting magnet. Magnetic nanoparticle in a size about 50 to 100 nanometer behave like a super paramagnetic material, i.e., in the presence of magnetic field, it's going to have an induced second field. If we turn off the magnetic field, then there's no magnetic field anymore. So in the presence of superconducting magnet, we expect this magnetic nanoparticle is going to generate the secondary field. And this field is going to perturb the water-prone behavior around it. So the key is that how can you emphasize, how can you maximize the influence of the induced dipolar field to the surrounding water proton? It turned out to be a very fundamental physical chemistry problem, and I will share some insight with you later about how can we have very sensitive detection of this very tiny amount of magnetic nanoparticle. Step number 8, of course, we have to put everything into usage. So we put a mice is in vivo measurement into NMR, so on and so forth. And then step number 9, we can have some kind of mathematical data processing, and that's the copper slide and also the carry home slide. To the left, these are the state-of-the-art method used in hospital all the time. T1 weighted, T2 weighted, and T2 star weighted imaging. As you can see, there's a tumor on the right side of the mice, pancreatic cancer, which cannot be light up so well. But for our method, we call it active feedback method. By spin dynamics and also by data processing, we're able to light up these two tumors, and these two results are based upon two different experimental parameters without going to the details. So it shows that perhaps this preliminary result shows that our method maybe has a better chance to detect low concentration and therefore early stage of pancreatic cancer. We are right now learning more about how to create orthotopic pancreatic cancer model, and we found that the website of the Hirsch Foundation is very useful because there are some slides about how to create this pancreatic cancer animal model. And more than that, we are thinking about, especially we heard from a lot of stories like Steve Jobs and so forth. For outside the lab, it seems that pancreatic cancer is unique in a way, even when detected at the early stage by show strong resistance to chemotherapy and radiation therapy. So idea is that can we also cure pancreatic cancer? My colleague, organic chemist, he made prostate cancer very successful. He told me that the problem for cancer therapy is because the cancer drug is so powerful, it kills everything. He told me it's a very toxic chemical, so on and so forth. So he advised me the key maybe is to deliver those toxic material to cancer specifically without hurting healthy cells. So our idea is the following. We want to create a new kind of chocolate. This kind of chocolate is made by, to your right, polymer, dentrimer to be exact. These are very loose bound polymer, no chemical bond, so it can easily melt at a very sharp range of temperature. Just like chocolate, they will not melt on your palm, but they melt in your mouth. Why we want to have a chocolate made by polymer? Because inside the polymer, we want to put cancer drugs and magnetic nanoparticle at the same time. Outside this chocolate, if you like, we want antibody in a conventional approach, and also some protein can trigger endocytosis. So our idea is that we can do exactly the same thing, deliver into and attach to the pancreatic cancer cells. Then trigger the endocytosis to eat it, and then we are going to turn on external magnetic field through the coupling, we call it Zeeman effect. It can start to heat up the magnetic nanoparticle. We cannot heat up that much because when you increase the power, you will start to heat up and cook the human patient. So this kind of coupling will be very selective. You only heat up magnetic nanoparticle just a little bit, and then hopefully it can start to melt and release the cancer drugs inside. That's the entire idea. Does it work? We have some preliminary result. We try to inject it to a lymph node. I heard from some talks that actually lymph node is the place to store such as cancer, stem cells, so on and so forth. So why not? Let's start with the lymph node. So we put an ensemble, the chocolate with cancer drugs and magnetic nanoparticle, where magnetic nanoparticle serve as the molecular beacon and molecular bullets, if you like. We try to kill the cancer stem cell in lymph node. As you can see, as time evolves, the small signal there, as I circle, start to degrade and disappear. That means that the stuff we try to target start to disappear. Of course, this is a very, very preliminary result. It's too early to draw any conclusion from it. And of course, there are some key concepts I do not tell you much about this yet. But before I continue, I forget to set my alarm to see how much is time. How much time?
You have plenty of time.
Plenty of time? Okay. So maybe I'll tell you a little bit about two key technology here. One is that how can you see that kind of small concentration of magnetic nanoparticle? Question number one. Question number two, how do you selectively couple energy to the magnetic nanoparticle while keep the human temperature intact? These are key technology based upon physical chemistry. First technique, how can we see those very diluted magnetic nanoparticles? These are the concentration from these three gentlemen. Jimmy Walsh right now is a professor of chemistry in Miami University, postdoc with me. Dr. Sandy Depa right now continues his second postdoc at Harvard Medical School. And Suji Huang is a residency at Harvard Medical School right now. The idea, we call it avalanche amplification. The physics is very common to us. So if I did not do it carefully, say if I make the gain of amplifier larger, and then if I speak a bit louder, and you start to feel some noise, because through the speaker, it's going to pick up the signal with a positive gain, and after a few cycles, you start to hear some kind of noise and so forth. This is also the phenomena we experience when we have, we call it avalanche amplification. In an unstable state, if you perturb the system a little bit through the positive feedback, that small perturbation, like the snowfall, can easily become a disaster. This is the common feature for nonlinear dynamics, or if you like, in chaotic dynamics. And also this is the famous, we call it the butterfly effect. Change one thing and you change everything. And the only requirement is that we have to make the spin dynamic system become nonlinear and even become chaotic. So that when we perturb a little bit, this perturbation can be amplified, such as the butterfly effect or such as the avalanche amplification. Okay? There's only one big problem here is that there's no such feedback mechanism in magnetic resonance. So it's important for us to think about how can you pick up the magnetization signal and make it become a strong feedback to create avalanche effect. Our idea is that this magnetization is going to induce current by processing in a coil of magnetic resonance. On one hand, this current got amplified and Fourier transform becomes spectral and imaging. On the other hand, perhaps we can build a very expensive noise cancellation earphone. That is, we can pick up the signal from outside and amplify. And for this $200 device, it feedback to your ears by changing the phase 180 degrees, so that when you arrive your ear, it reaches a perfect distracted interference with the outside noise and the signal created by this device. So signal cancel out, you feel you are in heaven. But for us, we have to do two variations. First, this is the device work at voice frequency. We need a device work at 600 megahertz or 300 megahertz. That is the precession frequency of the proton. So we can excite proton effectively. By changing the frequency, it turns out that it scales up the response of this device. The second is that in addition to distracted interference, we prefer the capability of control the feedback gain, feedback phase, feedback timing, so that if you experience about NMR, in addition to very complicated power sequence, by modulating the spin degree of freedom or spatial degree of freedom, right now we have one more line of power sequence. We call it the active feedback power sequence. So we can write a power sequence to compute the execute, and we can control the feedback field at will. That's the circuit. And that's what we made at the time, electronic circuit, without going to the details. So if you like how it works, exactly just like the stone formation on top of Florida, found a very small difference in the moisture, velocity, and the temperature of the air in a hot spot in the surrounding area. From a feedback effect in no time, it started to develop into a snowstorm or a thunderstorm, so on and so forth. The working principle is about the same. It's been about 8 years already since the passing away of Professor Dan Kimmerson, and I miss him so much, okay? And I hope with the support of the Hirschberg Foundation, we are able to continue this work, especially we are at a very critical stage of put the target therapy into practical usage. And there are a lot of times I'm so tired. Maybe you noticed that on the background, that's me, and my postdoc work all night, and I still just cannot, I quit. So I stay on the background, okay. But I need to say that in this process, as an outsider, tumor for us are something totally new. We heard friends, we heard colleagues suffer from this awful disease, but we do not have too much experience. So I always say that it seems there's a veil between myself, my coworker, my group member, and the tumor until we start to encounter these real cases. And actually, I feel, there's a moment I feel so bad all the time because I see the mice die, my colleague die, so on and so forth. But somehow, at the end, I want to share with you that on this miserable experience, somehow I see some hope and some light as well, especially when I read this book, Chasing Daylight. Because at the time, I want to understand the situation for brain tumor. And later, just like I try to understand what happened to the real patient with pancreatic cancer. And I believe this afternoon, I'm going to have more real contact with the patient like that. So I try to understand how they feel to make my research become more real to me. So I read this book, Chasing Daylight. And I read this book because, the first two sentences really caught my eyes. It says, I was blessed, I was told I had 3 months to live. Okay, and I was so confused. Such a famous CEO from such a big accounting firm and died at such a young age, that's only about 54 age. And he got brain tumor, only has 3 months to live, and he was so blessed. And more than that, he claimed that's the best 3 months in his life. So I cannot wait. I want to know his secret. Just like CEO, he behaved like CEO. So he comes to a to-do list in the final days. And just two things I learned from him. The first thing, make the 3 months become the best of his life. He lived at the moment, and also he created perfect moments. I still do not quite know what he's talking about. Maybe when I was at his stage, I can know better. But I just want to say with extreme gratitude to the foundation and to co-worker, especially to MD here, really give us the guidance. I just want to say by ending that we are going to do all we can again to make it not only a dream, but by remembering those people who helped with our project until today, we are going to do our best to make it become reality as soon as possible. Thank you so much for such engaging, supportive audience. We appreciate it.